Hello everyone, I am Marwan Abdulati, a PhD student in the Department of Industrial and System Engineering at the University of Rhode Island. Our research paper is talking about an improved GPU accelerated heuristic technique applied to the capacitated vehicle routing problem. The presentation is organized as follows. Some introductory information about the nature of the problem and the different methods used for it are first mentioned. I'll discuss the reasons why we selected the genetic algorithms, the GA, for our approach. Then, I'll detail the methodology we followed and describe the algorithm we designed. Then the implementation of our algorithm on the GPU is explained. I'll also discuss how we executed it on benchmark problems and discuss the results. Finally, conclusions driven and possible future work is discussed. In the VRP problem, we assume a fleet of trucks with uniform capacities delivering items to a set of customers, and we seek the optimal set of routes for these trucks. There are many forms of VRP, for example, dynamic VRP, VRP with time windows, and capacitated VRP. The capacitated VRP is the most studied form of VRP, where the total customer demands cannot exceed the truck capacity, and customers must be visited only once. There are many methods to solve the VRP problem, but they can be divided into two types, the exact methods and the heuristic methods. Exact methods depend on directory searches, dynamic or linear programming. The positive thing about the exact methods is that they can provide optimal or near optimal solutions, but they require extended computational resources and they have limited problem size to handle, about 100 customers. Examples include branch and bound, branch and cut, and dynamic programming. Heuristic methods, on the other hand, have acceptable computational times and can handle larger problem size, but they can provide only near optimal solutions. Examples include Clark and Wright, taboo search, local search algorithm like the 2opt, and genetic algorithms. So why we specifically selected the genetic algorithm for our approach? GA utilizes reproduction features existing in nature, such as selection, mating, and mutation. Unlike other methods, they operate on a population of potential solutions, not a single one, which increases the probability of finding a good solution. Extensive researches have been reported to combine exact methods and GA. Recent hardware advances of graphics processing units, the GPUs, encourage this combination to help with long execution times and extensive computations by parallelizing the algorithms. For this reason, we adopt the GA and present a GA algorithm that is 100% running on a GPU. But before we go, we have to define the VRP problem. We are given a depot node, 0, at a location x0 and y0, and a set of n customer nodes at x1, y1, x2, y2, and so on. Each customer I orders a negative demand d sub I and is visited only once. The cost c sub ij between nodes I and j is the Euclidean distance between them. Our objective is to find the optimal path L star, which has the minimum total cost, and is defined by the below equation, where the L star is equal to the path that causes the summation of the costs Cij for I and j from 0 and n to be minimum. The figure in the right hand side illustrates a typical VRP solution for a problem with truck capacity of 10 for each truck. The depot node is in the middle of the figure, and from where all the trucks can start and end their trip to it. For example, if we take route 1 at the right upper corner, we can see that the trucks start from 0, moving to node number 6, 11, 4, and back to 0. The numbers next to the nodes represent the demand values, which we can use to determine if the track capacity is exceeded or not. The number next to the lines represent the distance between each pair of nodes. We can sum all of them to calculate the total cost of the trip. And in this example, the total cost of the solution is 114. In our algorithm, we incorporate a GA and a 2-opt local search into a hybrid algorithm for the CVRP problem. Like any regular GA, a population array is randomly initiated with each row representing a possible solution called individual. An individual is a sequence of customers separated by the depot node to count for the capacity. Evolutionary processes like crossover and mutation are applied to the individuals to update the population at each iteration t. The cost f sub I and t of an individual is the sum of the costs c sub ij within the solution. Individuals generated from the evolutionary processes are called children, can replace old individuals called parents only if they have less cost. Elitism concept is adopted to take the best 5% parents in the new generation. This helps maintaining good properties throughout the entire process. The second key element in our approach is the GPU. The GPU, or the graphics processing units, are multiprocessor devices that can run a large number of instructions in parallel. There were many developed GPUs even before 2006, but in 2006, NVIDIA unveiled their first GPU with CUDA architecture, which included new features that took away the need for vertex and pixel shaders that were used in graphics programming. Also, arithmetic logic units, ALU, were complied with the IEEE floating point standard, instruction set for general computation, and shared memory. The GPU and CUDA technology enabled standard computational representation and the use of common programming languages like C, C++, and Python. It improved the performance cost and energy consumption compared to similar implementation on CPUs. As a result, many applications are developed counting on CUDA technology, like medical imaging, computational fluid dynamics, environmental science, and the evolutionary machine learning frameworks like TensorFlow and PyTorch. It's quite interesting to talk about the special GPU architecture. From the figure in the right side, we can see some symbols with dotted lines, and these dotted lines tells that they are just virtual containers, not physically existing in the GPU, but it is used to further clarify the concept. We will talk about them from outside to inside. The first one is the device grid, which contains multiple blocks, which are also virtual, and these blocks contains physical existing components called streaming multiprocessors. These streaming multiprocessors contain hundreds of streaming processor cores, which are responsible for executing the threads in parallel, using automatic thread scheduling techniques. Threads can greatly exceed the number of cores. A block is an array of threads with width of 32 threads. The global memory is similar to the random access memory for CPUs. It's the largest memory in a GPU with size up to 16 GB in some products. It's accessible by all threads and the CPU as well. A shared memory is a small memory accessed in a block level at a very high speed. L1 and L2 cache memories have much higher bandwidth than their CPU counterparts. All streaming multiprocessors share a single global memory and an L2 cache. In our implementation, we use a device grid with hundreds of threads running in parallel and distributed as a two-dimensional array. The grid is divided into 5 by 5 blocks. Each block is a two-dimensional array of 20 by 20 threads. The program array elements are distributed over the threads to perform computations separately. This facilitates high throughput memory transfers in the GPU. The functions implemented on the GPU are called kernels and can be divided into two types based on how they deal with the input arrays. The first type handles the entire array operations element-wise, where a single thread handles a single array element. This leaves the total number of population size multiplied by length of individual operations running concurrently. Examples include cost calculation, selection of parents, and crossover. Type 2, on the other hand, handles the entire array operations with vector functions. A single thread operates on the entire row of the array, which leaves a total number of just population size operations running concurrently, which is way much less than the ones in type 1. Examples include duplicate missing node checks, capacity constraints, and mutation. We face some challenges and limitations of why we implement our algorithm on the GPU, because GPUs support only numerical arrays with homogeneous widths, which is not the case in the VRP problem, because in the VRP problem its nature is every individual represents a possible solution that could have longer or shorter lengths than the others. To solve this, all individuals are initialized with a fixed length. Additional genes inside shorter individuals are assigned to 0. Our algorithm implementation can be illustrated by the figure in the right side, where the problem data that includes the list of nodes IDs, their x and y coordinates, the demand values, and the track capacity is loaded to the CPU. The CPU takes this information and creates an n by 4 array where n is the number of nodes, and then uploads it to the GPU. The GPU calls its first kernel, which is the cost calculation, where every distance between every pair of nodes is computed by the GPU kernel, and create a cost array of size n by n. This array is saved in the GPU global memory since it's too large to be copied to shared memories. Then, the initialized kernel randomly initializes the population array, where each row represents a possible solution. Refining kernels check for duplicate or missing nodes, then insert depot nodes to account for capacity constraints. Then the fitness function is called to calculate the cost of every single individual. A binary kernel is called to create a pool of 4 candidate arrays by random selection, and they have the same size as the population array. The best 2 individuals in each corresponding row are selected to form 2 parent arrays with the same size. Every 2 corresponding rows of the parent arrays are used in a crossover kernel to form 2 child arrays. The crossover kernel is called where a standard k-point crossover is adopted, and then a random swap mutation is called to apply to the child arrays where 2 random genes in each individual are chosen to switch their locations. Then the refining kernels are recalled to adjust the generated child arrays. Here the 2 local search is called and applied to the child arrays to further improve the generated children. The cost of individuals is recalculated. Generated children enter the new population only if they have a lower cost than their parents. Then the final population is sent to the CPU for output. Some people may ask why we adopt the elitism concept since we already have the greedy replacement criteria. We can answer this by saying the greedy replacement compares the children with their parents only, not the entire population. If parents have very poor fitnesses and their children have better ones, the children will still be selected even if they have higher costs than some other parents. That's why we adopt the elitism concept to compensate this by carrying the top 5% parents to the new generation. To keep the diversity of the population, a unique kernel is used to remove duplicates. For our execution, we used a GPU hardware with model GeForce REX 2080 with 8 GB global memory, 2944 CUDA cores, and 1024 maximum number of threads per block. The algorithm runs in CUDA 10 environment. We use 400 threads to avoid 100% occupancy, and they are distributed as 20 by 20 two-dimensional array. We selected the population size to be 100, and for problems larger than 100 nodes, we use the stride concept as illustrated in the figure on the right side, where the green array represent the thread arrangement and the blue array represent the input array, like the population or the children array. And it can be seen that the stride concept can help the thread arrangement cover the entire array, even if it has a lower size than the input array. We applied our algorithm on common benchmark problems and to test it. We developed another version of the algorithm to run on the CPU for comparison. To measure the solution quality, we used the percentage gap, where the percentage gap is the difference between the obtained solution and the optimal solution given by the literature, divided by the optimal solution. A good solution is recognized by its low percentage gap value. The table shows the execution results obtained when we run our algorithm on different problems ranging from 16 to 76 nodes. It shows the CPU and GPU times in seconds per loop, the best known obtained from the literature, the obtained percentage gap from our algorithm. It can be seen from the table that we reached the optimal value of some problems, and we even get better results than the one documented in some other problems. Also, the table shows the great difference in execution times between the CPU and GPU, which increases by the number of nodes. The figure on the left side shows the obtained solution quality of the proposed algorithm on the GPU, and the figure on the right side compares the execution time of the CPU and the GPU. In this figure, we used logarithmic scale to show the subtle difference between the results and to enable the plot to accept the large values resulted from the CPU. Because in the GPU, as shown in the dotted lines, we can see the values can reach 50 seconds per loop, while in the GPU, the value are much lower than that and almost fixed around a specific value. We also tested our algorithm performance with and without the two ops. The figure on the left side shows the solution quality of our algorithm with and without the two ops, and it's obvious that the two opt has a great impact on the solution quality. However, the figure on the right side shows the increase of execution time if we use the two opt algorithm in our software. But this is an acceptable cost to pay to get a better solution quality. In conclusion, we propose a new hybrid algorithm that entirely runs on a GPU to take advantage of their special CUDA architecture for executing instructions in parallel. A 2-up local search is incorporated with a GA to solve capacitated VRP problems, the CVRP. Our contributions in this work are that we significantly improve the execution speed. While the CPU execution time exponentially increases with the number of nodes, the GPU time is very low. We also obtained optimal values of some benchmark problems and improved some best documented values for others. However, we need further investigation to improve the GA algorithm to obtain higher quality solutions, especially for large problem sets. This will include different crossover operators, different mutation operators like inverse mutation, and maybe we can test modified GA algorithms like cellular GA, the CGAs, and island model GAs. Interested researchers are very welcome to visit our GitHub repository to take a look at our source code, and please feel free to clone, test, and use our code. These are some references we used in our research. And thank you for listening, and if you have any question, please go ahead.